Noise will always be present in measurements, and so filtering comes into play. One thing that's helpful for filtering out unwanted signals is knowing the frequency of the desired portion. For example, if we're using a thermocouple to measure temperature changes in a room, we know that the temperature is going to vary slowly. So any high frequency components to our signal we could filter out because those are just unwanted noise and don't really represent the temperature of the room. Filters can be made with active components or passive components. Active filters can have amplification, whereas passive filters are always going to reduce the voltage of the signal. This is a figure showing an active low-pass filter built with an op-amp. We see instead of a feedback resistor, we have a feedback and capacitor in parallel. The impedance of a capacitor is shown here. Negative J over omega C. Omega is the frequency of the signal, and C is the capacitance. And this is equivalent to 1 over omega Cj. We also have the impedances of the other loads. Resistor 1 has impedance R1, and so that gives us that, and then when we combine the feedback resistor with the capacitance, we get the impedance for this feedback, which is the product of the two divided by the sum of the two, or RF over omega C RFJ plus 1. Now we want to find the gain for this system, and we know from our previous analysis that the gain is the feedback impedance over the input impedance. Substituting these values into that expression, we get that the gain is shown here. Examining the effect of this op-amp at DC input, so at constant input, we can take the limit of the amplification as omega goes to 0. And so we just get that the capacitor has no effect, so it's the same gain as if we didn't have the capacitor in the DC case. We can substitute that value into our expression above, and we see that the gain for this system is the DC gain divided by 1 plus J omega over omega C. So that's called the cutoff frequency, and it's defined as 1 over feedback resistance times capacitance. Since we have a complex gain, there's going to be some phase shift. This slide covers the magnitude and phase of our filter. Here is again the gain, and you can see it's complex. If we want to find the magnitude and phase, let's get the term J out of the denominator. So multiply top and bottom as follows, and we get, here it is in complex form. So the real part is 1 over 1 plus omega over omega C squared, and here's the complex part of the gain. The magnitude of the gain is found like this. So we have the DC gain times the square root of the sum of the squares of the real and complex parts. And that turns out to be this for the gain magnitude. So it's a DC gain divided by square root of 1 plus omega over omega C squared. And then the phase shift is inverse tangent of the imaginary part divided by the real part. So we end up with phase is inverse tangent of omega over omega C. So you can see that the gain and the phase depend on the components R and C, which determine omega C, and the signal frequency omega. Here are the gain and phase for the RC low pass filter. And you can see the two portions for this active filter. Amplification is the DC gain, and then the filtering comes from the denominator. Now the filtering is what we want to have for getting rid of high frequency noise. So as omega increases, our gain magnitude is going to decrease. So for this low pass filter, low frequency signals are going to pass through with amplification close to the DC gain, but then high frequency signals will get smaller amplification. Looking at this again, here's the gain. Whenever gain is referred to, it's often mentioned in terms of decibels. This is a voltage gain, and that is the ratio of the output voltage over the input voltage, each of those squared. And the reason for that is electrical power can be written in terms of voltage squared. And so it's common to talk about voltage gain as 20 log base 10 of the ratio, output to input. That's really only valid in the case that the output and the input have the same resistance, but nevertheless it's often used. So we'll have 20 log 10 of the gain. And that's the gain in decibels. So we have here the sum of these two terms. So we'll have the DC component and then the attenuation. So here's the DC gain in decibels. Now this term is always going to be greater than 1, the term in the denominator. So that means that this quotient is going to be less than 1. So this term is going to be less than 0. So we have the DC gain, and then it's always the total gain of our amplifier is always going to be less than that when we have non-zero input frequencies, and that's called the attenuation. If we wanted to see the gain at the cutoff frequency, we could plug omega c into the equation for the gain magnitude, and we end up with ADC over square root of 2. So it's a DC gain over square root of 2. Now that in decibels is negative 3.01 decibels. That being the attenuation. So at omega c, the gain is the DC gain minus the DC gain in decibels minus 3.01 decibels for the filtering. If we look at what happens whenever the frequency increases past omega c, this is approximately what the gain magnitude is going to be. And we see that the attenuation will double every time the frequency doubles, or the gain halves. So you see here, if we had 2 omega c for our input frequency, then the attenuation would be 20 log 10 of 1/2, which is negative 6.02. So that's twice the attenuation. Past the corner frequency or the cutoff frequency, the gain is going to decrease 6 decibels per octave. So every time the frequency doubles, the attenuation is going to double. And here that is plotted. So you can see the gain in decibels as a function of the frequency ratio, input frequency divided by cutoff frequency. Here you can see a little more explanation about the decibels gain, or gain in decibels. If that's 0, then there's no change in the signal. You can see 20 log of 1 gives you 20 times 0, so 0 dB. If we have positive gain in decibels, then that means the signal is being amplified. So here, if we're doubling the input signal, then we would end up with 6 dBs. And if we have negative gain in dB, that means that we're attenuating the signal. For example, what we just saw, if the output is half of the input, then that's negative 6 dB. And here is a plot of the gain in dB. So this is the attenuation. At low frequencies, there's no attenuation, so we have basically no change in the amplitude. And then at the cutoff frequency, we have negative 3 dB. Beyond that, the amplitude gain changes -6 dB per octave. Now there's also phase shift associated with this because we have complex gain. Let's look at the effects of phase shift on the output signal. If our input is A times sine omega t, then our output is going to be some amplitude times sine omega t plus phi. Since we're only looking at the phase shift, we'll just say that there's no change in the magnitude, but the phase is going to be shifted by the angle phi. Now what if there was a linear change in phase with omega? That would look like this. We have omega t plus c times omega. So as the frequency increases, the phase shift increases proportionally. That's equivalent to a sine omega t plus c. So you can see that that would just be a phase shift, or a time shift rather, shifted to the left by this constant term c. Here that it is shown graphically. If we have an input signal sine of 2t plus sine of 3t, it would look like this. And if we were to shift that, have a linear shift, then the output would be sine of 2t. Here, capital C is 0.4. So our phase angle is 0.4 times 2 for this frequency component, and our phase angle is 0.4 times 3 for this frequency component. And the result is plotted in green. You can see that it is the same as the input signal, just shifted in time. Now if we had a constant phase shift, so if it was independent of the frequency, that would look like this. So say our phase shift was 0.8, we would have 2t plus 0.8 and 3t plus 0.8. And in that case, we don't get an exact or shifted output signal. It ends up being distorted. So you can see that in the red plot here. An actual filter, remember, the phase shift was given by inverse tangent of frequency divided by cutoff frequency. So that's not linear, and it's not constant either. So we're going to get distortion. Here's a Bode plot of the filter gain. We have the magnitude in dB, which we looked at earlier, and here is the phase angle in degrees. So at low frequencies there's no phase shift, and then when we reach the cutoff frequency there is 45 degrees, and it goes all the way down to 90 degrees at high frequencies. An amplifier versus a filter has two different applications, meaning that they have different desired results. An amplifier, we want to have, or different desired behavior. An amplifier, we want to have gain that is independent of frequency, so we would have the same amplification for all frequencies. And what we end up with is that there is some change in amplification at frequencies, or at different frequencies. For a filter, we want, for the pass band, here's a low pass filter. In this area, the pass band, we want constant gain. And then what we would like would be after this pass band to have zero gain. Or I'm sorry, yeah, zero gain. And we want to have a phase shift that's either zero or linear, so that we won't have distortion from our filter. And of course, the actual output of a filter is different from this. We do get relatively flat gain in the pass band, and instead of going to zero immediately after the cutoff frequency, it starts to drop off at a certain rate. And the phase shift can be nearly linear for small intervals of frequency. So if you're just looking at small range of frequency, then the phase shift in that range is nearly linear. Filters can also be made of passive components, and in a passive filter there's no amplification. Here is the differential equation governing the filter shown here, this RC low pass filter. You can see that V0 is the forcing frequency, or the input signal, excuse me. And so here's the output. What order system is this? This is a first order system, so we have a first order differential equation describing the time response of the system. V is the output. Now if we wanted to have the harmonic response of this system, then our forcing function would be sinusoidal. So we had that shown here. The output is going to be the time response will be the sum of a homogeneous solution and a particular solution. And those are shown here. The homogeneous solution is transient, so it goes away as time increases, and we're left with the forced response. The gain of the forced response is given by this quotient, so it's the input magnitude divided by square root 1 plus omega RC squared. And then the phase shift is given by the inverse tangent of omega RC. So if the input frequency is 0, then the gain for our low-pass filter will be 1. It'll be V0 over 1. So the output amplitude will be the same as the input amplitude. But as the frequency increases, then our output amplitude will always be less than the input amplitude. Here is the gain and phase shift. These plots show the gain and phase shift, and these are a little bit different form than the plots we saw earlier, since these are not plotted in terms of a frequency ratio, but rather in the product of omega times RC. For this passive filter, we had the same cutoff frequency as for the active RC filter we looked at earlier. Omega C is 1 over RC. If we were to want to find the gain at the cutoff frequency, we just substitute 1 over RC for omega, and again we end up with negative 3 dB. So the gain is 0.707, which in dB is negative 3. We can have a sharper response after the cutoff frequency if we cascade these filters. So if we cascade components, we end up with a second order system. And the natural frequency is 1 over RC, and here's the damping ratio. The gain is given by the ratio of V0 to the magnitude of our output V. And if we were to plot that, we see that it has a sharper attenuation as frequency increases than the first order filter. And also now the phase shift is shifted twice, so instead of being negative phase shift, we end up with a positive phase shift. So we have a steeper roll-off, which is the amount that the output decreases as the as the frequency increases, and a double phase shift. This plot shows the gain in dB versus the frequency ratio, the input frequency divided by the cutoff frequency, and the different lines show the different orders for the filters. The first passive filter we looked at was a first order, and then we looked at 2 that were cascaded, so that was the second order. We could have even more to get higher order. And you can see that the attenuation has a steeper slope the higher order filter you use. Again, at the cutoff frequency, they're all at negative 3 dB, but then beyond that, the slope is 6 times n dB per octave, where n is the order of the filter. So for a first order filter, again 6 dB per octave, just like the active RC filter. For second order, we have 12 dB per octave, and for fourth order, we would have 24 dB per octave. And the phase shift is proportional to n. So here's the phase shift at input frequency, and as we have a higher order system, we're going to get a more pronounced phase shift.